All right, let us begin with a prayer for the first time, possibly the second. We thank you today for this time we have to meet together, study math, and we just pray that you be glorified in what we do, Lord. In your name I pray. Amen. All right, so I'll start at the start. Ultimately, our goal is to understand a little bit about manifold theory, and if we're really lucky, a little bit about how geometry and topology interface. So let's just start out with what's a manifold. And I'll be, and so basically here, what we have is some sort of abstract set M, right? And the thing about a manifold is you have this collection of charts, right? And the chart is a mapping, say, from U, and here's V, right? And so usually I use an X, and maybe this one's Y. So these are the charts. And these will be mappings down to Rn. Let's say Rm. All right. Now, there's all kinds of technical nuances I'm probably glossing over here at the moment. I think we need to assume, a lot of people start with a Hausdorff. They assume the M as a point set is Hausdorff. Maybe it's paracompact or something. I mean, it's a relatively benign topological space. It comes equipped with this atlas, this family of charts, which give you one-to-one homeomorphisms of the sets in M with open sets in Rm. And for a point like this on the overlap, right? So in the overlap, you can study these functions down here, the so-called transition functions on the manifold. Let's see here. So that would be what? How's that go? Today's not a good thinking day for me, I should warn you guys. I have said some things to linear algebra students already today that are so very, very wrong. And so I'm not overly optimistic about my ability to do simple things like chase diagrams. You guys have to help me out.
Y composed with X inverse.
Y composed with X inverse, right. Now, technically, it's the restriction of that to a suitable subset for which the composition is well defined, right? Now, what makes this a smooth manifold is the assumption that these transition functions are smooth in the sense of mappings from Rm to Rm, right? So, M smooth implies that Y composed with X inverse is a smooth function from Rm to Rm. A convenient characterization of that, of course, is that the matrix of its Jacobian, its Jacobian matrix has partial derivatives which are smooth of all orders, right? So, now, that's actually just what I'm describing at the moment so far. I've just described two charts, X and Y, and I've described what it means for them to be compatible. Compatible charts are those which, when they overlap, we can say they're compatible if they overlap and they have smooth transition functions, right? We also need that X composed with Y inverse is smooth, right? The other way. So, an atlas would be something like this. It's the set of U, comma, let's say I need to start using an index of some sort. So let's say U, U sub I, X sub I, such that what? Such that the union, I equals 1 to however many there are, I equals to K, of U sub I is equal to M, and U sub UIXI compatible with UJ, XJ, whenever what? If. How about when ui intersect uj is non-empty, right? Of course, you could be greedier. You could just define compatibility. You could say two charts are automatically compatible if they have non-overlapping chart domain, right? And you can just say that an atlas is it's a family of charts whose domains cover the whole manifold and who are compatible. So a manifold technically is a point set paired with an atlas. I guess definitions vary. I mean, that's one idea. You can also talk about the so-called maximal atlas, right? So if you take what's the maximal atlas? No, I assumed a certain finiteness there that's not necessary, okay? I mean, you could have infinitely many charts, I suppose. If we assume that the manifold's second countable, and I think that's usually done, then you have a countable family of charts that would cover it. By the way, if you want to read about infinite dimensional manifolds, one place you can read is in Serge Lang's book. He actually tries to do these things without using RM. Rather, he just tries to do things using like smoothness of compositions of maps and stuff. And so he's able to say a fair amount about manifolds which are built over Banach spaces instead of just Rn. It's sort of a anyway. Okay, so well, the maximal atlas. What we do is just take a given set which meets the covering condition and the overlap condition, right? And just adjoin to it all other possible charts which are compatible with the initial set. And then I think what people usually mean when they say, I don't know, I'm not sure what people usually mean. I don't know enough people, but certainly you could consider the point set M paired with the maximal atlas. That would give you, I think that's what that's what I think of anyway. I think of a differentiable structure. But on the other hand, if you have an atlas which, maximally continues to the maximal, which continues to the maximal atlas, then that also sort of captures the same differentiable structure, right? Like, if you have something that, when you throw in the rest of everything that's possible, it gets you the maximal atlas. It's kind of, to me, it's kind of the same data. Obviously, it's more convenient in terms of actually proving things to work with not the maximal atlas, right? So an atlas gives you a set of coordinate systems that covers everything, and locally allows us to do calculus. That's the big idea here, is that this setup allows us to do calculus on the space, right? So that's the thing. So do you guys think of any examples of this?
The unit circle?
The unit circle? Is it? That's a difficult example. I was looking for easier examples.
R2?
R2, yeah, okay, fine. No, I mean your example, M equal to the unit circle, is a good example. So it's a subset of R2. Of course, you could take M equal to, say, Rn, right? This is a manifold. If you pair it with, you can take the atlas to just be what? It's kind of stupid. You just take the Rn paired with the identity, right? So there you go. This the Rn paired with the Cartesian coordinate chart is in fact a manifold. While I'm on this cavalcade of boring examples, vector space. Any vector space is a manifold. It's a linear manifold, in fact. And the atlas, you can just, with basis what? Basis beta, let's say. Well, then my usual coordinate chart, right, phi beta, which is a mapping from what? From V to Rn. Well, guess what? I've been using that terminology meaningfully. A coordinate chart in linear algebra is an honest-to-goodness coordinate chart. It's mapping from the vector space to Rn. It's a Now, in principle, if you think about like, okay, so what's the maximal atlas for a vector space, right? Now the maximal atlas for a vector space, if you think about it, it will actually include things that wouldn't be coordinate charts in the sense of linear algebra. There's no linearity condition on our coordinate chart, right? Just smoothness. So you could have weirder stuff in the maximal atlas for a vector space in the sense of manifolds. But it's also the case, of course, that every possible basis produces a different coordinate chart, and those would also be in the maximal atlas. So you could also look at like refinements of atlases. You could look at like, I want an atlas that only has in it coordinate charts in the proper sense of linear algebra. That's what we do in linear algebra, right? We don't allow coordinate charts which are weirdo, nonlinear things. We insist that every coordinate chart is built from a basis, right? If you're working in some other corner of geometry, you might insist that all your coordinates satisfy some condition with respect to some object which is sitting around, like something about the metric or contact structure or whatever else you have to work with. Now so Nathan had one interesting example. How about this? If we have a matrix Lie group, so something like basically A in, say, R n by n, like n by n matrices, that satisfy some condition, like f of A equals to 0. So there's some defining condition some equation that has to hold for the matrices. Then this kind of thing will typically form some sort of manifold.
Should have just done the minimal polynomial. It would be sooner.
So for example, it could be like A transpose A minus I equals to 0, right? If that was the case, then we'd be looking at so-called orthogonal matrices of order n, right? Or ON. Now it becomes a more interesting problem to actually find find explicit coordinate charts on this, right? Let me take something. I'm not actually going to try to produce a coordinate chart on here. I mean, we could, but let me just work on something a little bit simpler just for a second. So how about SL2R? So this would be like A, B, C, D, such that what?
A plus D is equal to 0. Oh, sorry, no, that's...
Yeah, okay, you're thinking little SL2.
Such that the determinant of A is 1.
So we got AD minus BC
is equal to 1.
equals to 1. As I'm often wont to do, I work myself into a corner. Like that. You're like, I'm tired of that pun. Find a new one. It's one of the great problems of teaching physics this semester. It hasn't given me proper time to think of new jokes. All right. So you can, this is, in fact, we can prove that this is a manifold. This is going to be a three-dimensional manifold. Because, and this is just counting, you have 4 real variables, right? You've got 1 real equation. It's a three-dimensional manifold. Now I can ask, what's a coordinate chart in the neighborhood of the identity? So the identity, of course, is what? The 1, 0, 0, 1, right? So here I have AD, right, not equal to 0. If I'm close to the identity, right? Or I could look at, well, let's see, maybe I can look for something like, how about A not equal? Let's be more special. Let's look for A not equal to 0. Well, I'm gonna make D not equal to 0. Whatever. Okay, so I've got A is equal to what? 1 minus, or 1 plus BC, right? Divided by AD. for d not equal to 0, right? And so my coordinate chart, say x, on A, B, C, D, is just what? Well, I mean, I guess what I would do would just be BCD. Of course, A has, I mean, it's implicit within the context here that A has to have that format, right?
So you're saying it's three-dimensional, the fact that, you can choose any three other variables, and then you just don't have a choice in the other one?
Well, let's see here. There is, oh, by the way, this, well, we can think about its dimensions some other time. Let's see here. So you'd say I've got U equal to what, like A, B, C, D, such that what? Such that D is not equal to 0, right? And then you could look at other charts, right? You could look at like V, A, B, C, D, such that, I don't know, I guess A not equal to 0 is another one you could look at, right? That would have what, x of so I can divide by A in this case, right?
So you have ABC here.
So I'd have what you say, A,
Which is ABC.
ABC,
Yeah.
and what was D was equal to what here?
And
1
it's equal
plus
to 1
BC
plus
over A.
BC over
What, oh, 1 plus BC over A. So I guess if I was to picture what's going on here, right? And it's kind of hard to picture a three-dimensional.
Yeah.
This is just heuristic picture. Here's the identity, right? And there is some overlap, right? Like this is U and this is V. They both of these charts contain the identity, right? Because they both have
and D different than 0.
right. So you could consider the overlap of these two charts, which would be what? Right? And you could ask, what's the, you could pick a particular ABCD like we did, right? And you could compare, oh, I guess I should really call this, X is probably a bad choice, yes? Maybe we should call it Y. Right? And so we could compare X and Y. Right, so for a particular point in here, which I have, this is A, B, C, D, right? We get what? On the one hand, we get under X, we get B, C, D, right? Under Y, we get what?
So ABC.
ABC. Right. Go from here to here, we would be studying Y composed with X inverse, right? In particular, we have Y composed with X inverse of BCD is equal to what?
ABC.
But we shouldn't write ABC, all right, because that is not constructive. It's hard to judge smoothness. I mean, I feel like I had another cough in there. No. So traditionally, if we're going to write a formula in terms of the domain variable, we should write in terms of the domain variables. So that's where.
It would be 1 plus BC over D.
Right.
BC.
What do you say?
BC.
BC. Then the question is, are those smooth functions from R3 to R3? I think for the second two components, manifestly so.
Yeah.
And for the first component, well, it's a rational function of the coordinates, where we're in the place where d is not equal to 0. So yeah, we're good to go. Smooth. And so that shows that these are compatible charts, in fact. I like this example. This example actually is not too bad. It actually has something to it. Now, I guess the question is, does that cover... Now here's the harder thing, is like, what, do we need another one to cover all of SL2R? Does this get everything in SL2R? I don't think so, because we could have like... You could have like 0, 1,
-1.
yeah. You can have those kinds of things. Okay. And that is not, that's out here, right?
Yeah, but in that case, B and C would have to be non-zero, so we can.
Ah, right.
Yeah.
Yeah. Oh, exactly. So then we can construct two other obvious charts using the fact that B or C, the product of a BC must be, if AD is equal to 0, then the product of B and C must be 1. So either have B is equal to, you know.
Wait, would they have to product equal to -1?
Hmm?
You said 1. Would it have to be -1?
Yeah, -1.
Sorry.
Now we had more interesting examples earlier in our discussion this semester. We talked about projective spaces. I mentioned we actually looked at like the homogeneous coordinates on that. We had some more interesting examples, but I think that's enough to get some sense of what I mean by manifold, right? So the next step in this game, right, is to talk about what's the tangent space, right? So what is the? I mean, I guess the next step in the game is to talk about what's smoothness of mappings and stuff like that, right? So if you have two manifolds, I should probably talk a little bit about smooth maps. So if we have two manifolds, right, M and N, and we have a function going from one to the other, right, then that's said to be a smooth function if all its local coordinate representatives are smooth. So in particular, that means that if you look at the coordinate chart here and the coordinate chart over here like that, then down here, which would be going from, say, Rm to, let's say, Rn, supposing that's an m-dimensional manifold and that's an n-dimensional manifold, then this local coordinate representative, which would be what?
Y of f of x inverse.
Very good. So this would have to be a smooth map, right? In the sense that the Jacobian map, you could look at it this way, the Jacobian map of this mapping, right, has smooth partials, right? Or I guess to be more specific, if you look at the ijth component, that's an element of C infinity, Rm to Rn, right? For all ij, then that would give us smoothness of the Jacobian map and hence the smoothness of the local coordinate representative. And then by definition, or theft, depending on how you want to look at it, smoothness of f. Special case, right? If n is equal to r, right? Or also, honestly speaking, if n is equal to Rm, you don't really need the y. You can just use the identity mapping in the case that n is like Euclidean space. So in particular, that's important because one special kind of mapping, is if you have, I feel like this, R, right? So if that's your f, or let's not use f, let's use phi, right? Then to say phi is smooth, phi is a path, right? Other way around, huh? This would be a function. I need another picture. Oh well, I'm getting too greedy. Let's try this again. Another picture down here. Now, excuse me. I haven't finished the thought here really. That's a smooth function from m to n if that's true for all possible coordinate representatives. Fun fact, if you can prove that you have smoothness with respect to one atlas here and one atlas there, it will be true for all compatible atlases. It suffices to check smoothness on one pair of atlases. Or point-wise, if you check smoothness with respect to a chart here and here, if you get smoothness, then any other pair of charts which is compatible with the initial pair will also give you smoothness. It's not hard to prove that, because if you have y composed with f composed with x inverse is smooth, then all you have to do is like composed with x bar, composed with x bar inverse, and composed with, let's see here, y bar inverse composed with y, then that will equal, how's it go? Oh, I think I've done this the wrong way.
I mean, if there's an overlap, then...
Curses. I have to draw a picture. What's that? Yeah.
I don't know. Erase it.
Oh, sorry. Yeah, what I was trying to say is if I also had this, right? Another coordinate system here and another coordinate system here, right? I could look at the local coordinate representative like that, which would be
Y bar. What's with that?
and then you can relate this to that. Right?
Right.
So,
And where there's an overlap between like the y and y bar, there's the like y bar composed with y bar inverse. Those are just the identity.
right, these are so-called transition functions. So transition functions on n and m respective. Those are assumed to be smooth. I mean, when I say that we have another pair of compatible charts, that is to say that those mappings are smooth. So yeah, if I have that smooth, I automatically get that that's smooth. So if I can just check smoothness with respect to a pair of charts which covers a given point in the domain and corresponding point in the codomain, I mean in the target space, then we're good to go. Now the other, of course, thing to talk about, which I should talk about just briefly, is if I got M, right, I can do, there's two kind of most very important kinds of maps. One is just a function, right? A function from the manifold to the reals, right? To say that that's a smooth function is to say what? Well, basically, pick a point P, right? Coordinate chart from there, like this. That gets you down here. Here's the, the range of the coordinate chart down in RM, whatever. And then you insist that this mapping, which is what?
F composed with x inverse.
Yeah, sorry, I'll get with it eventually. F composed with x inverse is a smooth map from Rm to R. That would give you smoothness of this function. And we say that F is an element of C infinity PM, something like that.
You said you can easily prove that. That's kind of like the proof that I think we did earlier, that if you can have an isomorphism, what was that? I can't remember. If you can draw an if you can find an isomorphism between two of them, that was sufficient enough to prove that that the other one was also smooth. No, wait.
Oh, this is a
Ignore me.
this is the definition, so don't
Yeah.
worry. We can't go wrong. Can't go
I can't.
wrong.
I can't remember for life
I
me what that
guess
was.
we can't go wrong. No, this is just definition at the moment.
Yeah, yeah.
This is what we mean. I mean, when I say a function's smooth on a manifold, what I'm saying is it's smooth when you run it through the chart structure,
Yeah.
basically.
Yeah.
And conversely, what's a path in a space? Like a path, if I have some, some other copy of R, right? And a path takes R and it basically pastes it onto an abstract set, right? Of course, you can talk about continuous paths, smooth paths, all piecewise continuous. I mean, whatever. I'm just talking about smooth path, like that. So this, I might call phi. So to say that's a smooth path assumes what? We would need
X composed with phi.
this guy, right? Yeah. So you said X composed with phi?
I think so.
I would need that to be a smooth path into RM.
It's 4:00 p.m.
Shut up. She never shuts up. I'll take away her batteries. Let's see how she lives. She'll come back. Some student will come in here, put the batteries in when I'm not around.
It's like Furbies. You remember those?
Oh, Furbies are so creepy.
Even if you took the batteries out of those, they'd always wake up in the middle
There's a
of the
few
night.
toys we have like that at our Sunday school. even after the batteries are out, they've got some capacitors in them or something, and when you run the wheels, it ends up charging the circuits, and then like there's this particularly ghostly Thomas the Train it's quite loud, and it's just all of a sudden like doo, 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 doo. It's awful. Awful. Okay, so that's how we do calculus. I mean, basically, and then of course, next thing on the list, how do you define a derivative? Like, what's the partial derivative with respect to the manifold coordinate xi of a function, right? So let x be a mapping, say, from U to Rn, and x equal to, say, x1, x2, xn. So we write indices up in here. Ah! What did I just say? What did I just say? Indices up. All right, there we go. So this is, this, if I act on a function, right? It's partial derivative of f. So to be more precise, if I have this at a point P, and I'm differentiating a function, that's defined to be partial ui of the function of x of u1 un. And then at the end of it all, I'm supposed to put in u equals to what? So the picture here is like up here, we've got the point P, right? Then they've got this coordinate chart x down here, x of P. And I'm thinking that basically x of P is equal to u. So the coordinates down here are like un through u1. I use the u's for the Cartesian coordinates in down there, whereas the x's are up here, right, in some sense. So u is equal to
X inverse.
I think x of P, my current notation.
Oh yeah, right.
Yeah. Just a larger question is, did I do it right? Let's see here. Does that make sense, what I wrote?
Yeah.
So basically No, that doesn't make sense. Does not make sense. Mm-mm. It's more striking, this definition, if you write it like this. See, this doesn't make sense. X doesn't act on tuples of U's. U is down here. X inverse is what I want. See, because X inverse does take U's as its inputs and produces for me points around P. All right? So this is supposed to be inverse. Sorry about that. I mean, so again, it's theft. What we're doing is we're taking the function from the manifold to the reals, and we're trading it for a function. Right? We're basically just changing it to a function of the RM, which is under the manifold, right? Where we can do partial differentiation as usual, and then so of course there are lots of things you can prove here. One particular special example of f would be when you have f of p, right, is equal to x, say j of p. In other words, if f is your jth coordinate function, the jth coordinate function, well, that's a function that goes from a neighborhood of p in the manifold, right, to the reals. So we can calculate the partial derivative of it, right? And so, like, if you calculate partial f, partial xi, at the point P, it's something like partial ui, right? Of, well, I'm supposed to do xj, right? Of x inverse of u1 un, and then after all of that, I do what I put u equal to x of p, fine, whatever. So the question is, what is this?
It's just partial u j partial ui.
Yes. Now, in a given it takes me more or less time, and then this is stupid because that's a constant. So. Now, why is that uj? Right. So it's the inverse, I mean, think about it, it's the inverse image. So this right here, right, is x of p is equal to u1, u2, let's say un, right? So then what's xj? So then p is equal to what, right? So p would be equal to x inverse, right, of u1, un, and then what's x inverse? What's x sub j of p, right? Well, that by definition is uj, right? But it's also this. Really, it's just coming to terms with what we mean by coordinate function. It's the jth coordinate function. But there you go. What that shows you then, like, if you allow me this small Menga-style calculation, is that partial xj, partial xi is Kronecker delta ij. So again, we get the, in other words, we have sort of independence of the coordinates on the manifold in the same way as we have independence of Cartesian coordinates. All right. There's a chain rule. All right. Something like here, if I change coordinates, I can relate the let's see here. Sorry, I was about to get off the tracks there for a minute. That's good. All right. So next up, finally, the tangent space, right? What's the tangent space look like? See, I'll get straight to it. I would say the tangent space at the point P to manifold M, we can define to be, there's like 3 or 4 different popular views. I think since we're working in the smooth category, we have the freedom to use derivations, so let's do that. It's going to be xp, an element of the, well, let's say xp, how to say this cleanly, xp such that xp is a derivation on the set of smooth functions fe. What does it mean to be a derivation? So in particular, xp of f times g is equal to xp of f times g of p plus f of p times xp of g. So it's Leibniz, it satisfies this product rule. And what else is it? Also xp is mapping what? Is xp is mapping from it takes functions and gives you back numbers. So obviously, I mean, example, okay. If we have M with, say, U X coordinate chart, right? Then you can look at partial x, say I, at the point P, acting on a pair of functions, and you can prove that in fact that's partial f partial xi at p times g of p plus f of p times partial g partial xi, you know. In other words, and also of course, right, I mean, so let's just say collectively these, we say xp is an element of the derivations of p of m. Derp. Anyway, so certainly the partial derivative with respect to a manifold chart is a derivation. Right. How do you prove this? Well, I won't go through it, but basically this is defined in terms of lifting what? The ordinary partial derivative of the product of functions. So, I mean, this is almost immediately after you notice that if you take fg and you compose that with the inverse mapping, that's equal to f composed with the inverse mapping producted with G composed with the inverse mapping. That's not composition, that's just product. And so, because of this identity, when you take this partial derivative in terms of the the variable down on U, variable down in Rm, you get the ordinary product rule down in Rm. You do that, and then you lift it back up, and then you've got the product rule on the manifold. The chain rule is similarly proved, although at the moment I'm struggling with, do I want to state the chain rule just yet? I don't know if I want to or not. Okay, so then next question, right, is that everything? Are there other kinds of derivations, right? And the answer on a smooth manifold is no. Pretty much the derivations at a point you can build from a coordinate. I mean, let me be more technical. There's a theorem, which I won't prove, which states this: if x is an element of the derivations at P of manifold M, then x is equal to the sum, I equals 1 to n, of x acting on x upper I, partial partial xi, at the point P. And I guess since I'm sticking p's on stuff, I'll put a p here and a p here also for good measure. In other words, the tangent space, right, at the point P is a real vector space of dimension n, and the coordinate derivations we can use as a basis for it. In other words, TPM is the real span. Now, of course, we're never content to just stop with tangent spaces. We also want to look at their dual.
What spaces?
The dual, yeah, the cotangent space, right?
No.
The cotangent space, TPM star, or just, sometimes it's also noted this. I can't make up my mind. Anyway, let's say that this is alpha mapping from TPM to the reals, right? Such that alpha is linear. So, you look at something like alpha acting on, say, x, p as above, right? Well, that would be like alpha acting on the sum, I equals 1 to n, of x of xi, partial partial xi at point p, right? By linearity, you pull out the sum and the coefficients, right? And typically this, all right, so common notation that I'm always a little bit scared of using with math students, because you guys are not as immersed in this culture, but this is x upper I. It's the ith component of the, I mean, technically at p, I don't know, I get tired of putting the p, fine p, that's all at p at the moment. So, I mean, this is, I'm tired of writing the p. Oh, fine. I'll get over it eventually. And this, on the other hand, is the alpha lower I. No, I don't want to write the p. Fine. Haha. Dead. So, this we can write as the sum I equals 1 to n of like x upper I, alpha lower I. And if you're a proponent of the Einstein summation notation, you drop the sum and you just say it's the contraction of the components of the vector x with the dual vector alpha. Now the dual space, right? We also have to say, okay, so how does, at some point or another, excuse me. Now here's what I'm forgetting is whether I need to introduce the exterior derivative here or the differential, or maybe both. But this much is true. If I have a function, right, and that's a function from m to the reals, then I can say df is a function from the tangent space of Pm. To the, well, I guess you might be tempted to say from more general for more generous reasons fp of r, but I think this is the place where we're going to identify that with r. And what's the definition? What's the definition of this differential going to be? We're going to say dpf acting on x is equal to what? X of p. I wasn't looking at you, I was just looking at the clock. Gotta be a number.
7.
Dang it, Joe.
Sorry. And 2.
Joe came to check on the pizza party yesterday. I was like, I was gonna do it, and then I was thinking about arranging it, but then Daniel told me with authority yesterday, not you, the other Daniel, my son, and he's like, Wednesday we're having pizza because it's a it's a Wana night. We have pizza before Awana. And he said it with such authority, I believed him. So I thought I want to have pizza earlier in the day and have pizza later in the day. Shouldn't have listened to him. Rabbit soup. So, long story short, I still owe you guys a pizza party since you definitely made a legitimate effort on the advanced calculus homework last semester. I mean, doesn't the advanced calculus homework last semester make that conversation that you just had rather silly about linear? Whatever conversation is that I'm not supposed to know about. I'm just saying.
Oh, we didn't. I didn't know.
Oh, you weren't there? It was just okay.
Yeah, that was
Because
Michael.
I could be. Oh, it's just Michael. Okay. I mean,
Why was Michael there?
it could be so much
He's
worse.
graduating.
Oh, yeah.
I'm very restrained in linear. I'm very restrained. I don't. If I had my druthers, I'd do a half a semester of differential forms and like wedge products. I mean, it's linear, sort of.
There would be no engineers left
I
in that
behave
class.
though. I talk about linear algebra. It's just hard linear algebra.
I was trying to look back at your old stuff for quiz 2 compared to what we're doing on this quiz 2.
You can't compare
You,
those.
there's
Our
no
quiz
comparison.
2 was like, it was just vector space stuff.
Yeah. I look back and I was just like, oh man, like, no help here.
We should mature.
I was just like,
So
that was crazy.
this is the definition. That makes sense, right? Because the derivation eats a function, gives you back a number. So like, yeah, I'm definitely gonna get a lot of marker on shirts in the years to come. Who am I kidding? This is my office for how long? I mean, this is my 6th or 7th move since I've been here. So, I like where I am. I want to stay here, but I'm also a realist. So my point is, all right, as we talk about the push forward, right, or the differential, if you like, in the larger context, then this doesn't quite fit with it because the output's a number, right? Basically, there's an identification here, which is that we're setting the basis for the tangent space at R, which would be partial partial t, or ddt if you like. We're just really setting that equal to 1. That's the identification which is being made here. Okay, so anyway, with that, of course, then you can define for the coordinate differential, right? This is what? Right? Or if you like, just x upper j. So the differential of the coordinates is picking off the jth component. Now, if you should recognize this behavior from linear algebra. What we're looking at is a dual basis, right? So it follows. Let's see here. If I take this and put it back up in the line above, then I get what? Alpha is equal to a sum of alpha acting on partial partial xi at p times what? Times dx upper I. Like that, yeah. So I'm just, oh, fine, one more step. This was alpha of x, right? So it's really this, but the point is I can, like that. It's the sum of these numbers times those maps acting on that. So then you just strip off the x, and then what we of course then have is that the cotangent space to M is what? It's built from the span, the real span of dx1 dxn. And now we're off to the races, right? We can start taking wedge products of these and building differential forms over the manifold. And we can start looking at the push forward of vector fields and such. Let me do that. Let's see here. So now, if we have manifold M, manifold N, right? And you can think about the tangent space being something like that, right? Tangent space of P to M, and then over here, the tangent space at F of P of N. You've got a function, a smooth function from one to the other, right? And then of course we've got charts, right? X here, Y there, let's say. RM, Rn, like so, right? If I have xp, an element of the tangent space of P at M, then we can define the differential at the point P of F acting on xp to give us a element, give us something over here, right? I can visualize this by thinking about, I've got this vector here, right? And I'm transporting it over to this vector dpf xp. Now, people who are more careful than I, and who would those people be? Well, lots of people. People with time to study things. How about those people? Here's one of those people. Smooth Manifolds by Lee. He makes a distinction between this thing, which I've been trying to call the differential, versus the push forward. If I understand his language correctly, when he talks about a push forward, he wants the push forward of a vector field to be a vector field. Or something like that. And so if you have f not injective, right, as you thought about